Thank you for coming. I was charged to prepare a presentation for a general audience, although I do recognize lots of our math students here. But I hope you at least will find it entertaining, and I can persuade those of you who aren't already studying math that it is interesting and pretty. Well, pure math anyway. Okay, so what is pure math about? Well, we want to understand structure. So we look at some system, and it might look really chaotic, but we want to figure out what's the underlying structure so that what we see makes sense. So let me tell you an anecdote. When I was a kid, my dad would drive us up to the Sierras whenever he could find a chance, and sometimes that would just be for a 3-day weekend. Now, mind you, this is an 8-hour drive each way. So I spent a lot of my childhood looking out the car window, watching these orchards go by, and I would look at them and think, why do the people plant them so randomly? I mean, how do you even figure out how to plant them that randomly? And then we'd get to this one spot, just for a moment, where I could see how everything lined up. And I'd say, does that always happen? So then I was more excited to look at the orchards and made my dad happy I was a little quieter. And what I also found is once we started to go up into the mountains that you get this kind of overview and you can better understand the system and the patterns in the system that way, at least sometimes. And so I posit that it's these insights and these moments of clarity that get us addicted to mathematics. Okay, so now I want to spend a few minutes exploring through images what we perceive as order and what we perceive as beauty. So symmetry is commonly quoted as something that, of course symmetry is beautiful. And here's a picture of a fractal, so this is actually a mathematical picture. And you can see lots of different kinds of symmetry. There's dilational symmetry, there's reflective symmetry, and you get a pretty cool picture. Here's a columbine. That's what we call it in the US, in the Rocky Mountains, where I came from. And there's a lot of rotational symmetry, and in the leaves, which didn't show up very well in that. And here's a sea urchin of some sort with a lot of rotational symmetry. Some other sea critter, again, a lot of symmetry. Yeah, kind of a scary looking sea critter, but it does have symmetry. And we also see a lot of symmetry in architecture. And yeah, you can't see the ceiling too well on this, but there's a lot of symmetry in the tiling of the ceiling, but also just in the arches. And this is the inside of a dome with lots of interesting symmetry because you have these pieces shrinking, but they're very much the same, just dilated differently. What else? A mosaic where we have reflective symmetry across this axis and this axis, at least in this piece. And then we've got translational symmetry. This guy isn't a reflection of that guy over there, but it's a translation. And same thing with those pieces. Okay, and here's a relic with a lot of symmetry. A mosque, very beautiful, and here's a close-up of one of the pillars. So you see lots of different kinds of symmetry in these different shapes. Ceramic tile with symmetry, covered walkway with translational symmetry on the covering, art, oriental rug, lots of different kinds of reflective symmetry, another oriental rug. Okay, now I hope I've worn you down on symmetry. Okay, it can be beautiful, so I hope you're tired of it. Maybe it's more interesting if things aren't completely symmetric. Maybe if we have some dissonance in there, it's more interesting. So here are 3 beautiful zebras. And this guy on the front part looks pretty symmetric in its patterns, but look at its bum. Isn't that cute? That's not symmetric, but it makes it more cute. And same thing with this guy. Its bum is not totally symmetric, but it's so cute. Now this guy, its bum is pretty symmetric. But look, the black stripe doesn't match up with the black stripe over there. It matches up with the white stripe. Black with white, white with black. That's kind of cool. Makes it more cute. Makes it more interesting. Okay, and here's a biological illustration, which well, each critter in there is pretty symmetric, and the layout is symmetric, except we don't have perfect symmetry. This guy is not the same thing as that guy. That guy is not the same thing as that guy. And I think it makes that picture more interesting. Okay, it's a sculpture by Moreau, not completely symmetric. It's a picture by Paul Klee. So we've got lots of elements of symmetry, right? That has a lot of symmetry in it. But as an entire picture, it's not a symmetric picture. Okay, here's another sculpture of Moreau. Okay, maybe there's too much dissonance in that. I think it's really cool. And here's a sculpture by Picasso, which I think definitely has too much dissonance. Kind of reminds me of a nightmare. Okay, so here's my hypothesis that I'm hoping I can convince you to embrace, at least for the duration of this talk, that a balance between symmetry and dissonance affects our perception of beauty. This is windblown sand, which has both some suggestions of symmetry, but a lot of dissonance, but I think is very beautiful. Okay, two more images. This is a picture by August Macke. So elements of symmetry, but not completely symmetric. And a picture by Kandinsky with more dissonance, because it looks just sort of like my room, kind of messy. So here's another hypothesis, that structure and elegance contribute to our perception of beauty. This is a picture by Modigliano, which I probably didn't say right, but forgive me. And this is a sculpture of Picasso that has a lot of structure and I think elegance. Another picture by Macke with a lot of structure. I think it's elegant. So these are my aesthetics when judging the art and beauty in math formulas and math proofs. I think it's interesting to have a balance of symmetry and dissonance, not just complete symmetry. And I also look for structure and elegance. Okay, and then have to admit that sometimes things that are random are actually beautiful. This is a card, I think it might be in Hungary. I thought it was cute. Okay, so now on to the math. Now that I hope I've convinced you of reasonable aesthetics in judging things. So what are some well-known beautiful theorems in mathematics? Well, there are some beautiful identities involving the functions sine, cosine, and the exponential function. So where's my little guy? This is the cosine function. So it just carries on repeating like that. So it's called a wave sometimes. And this is the sine wave. It just carries on repeating. So that's why there's a little fish, because those are waves. Okay, and here's the exponential function. So it just gets steeper, 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 like this. Okay. So we've got these expansions, these series expansions. So basically they're infinite degree polynomial expansions. So cosine of x can be written this way. And there's some elements of symmetry in there. So this exponent of 2 matches with this denominator of 2 followed by this exclamation point. So that's called 2 factorial. Here we've got a 4 matching with this 4 factorial. So 4 factorial is 4 times 3 times 2 times 1. A 6 and a 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, and so on. But there's the dissonance that these signs are oscillating. So we've got a minus, plus, minus, plus, minus, plus, and so on. And also always even powers here in order. And so the expansion for sine is somewhat similar, but we've got odd powers of x. By the way, 1 is x to the 0, 0 is even. And we define 0 factorial to be 1 just so that all our formulas work nicely. Okay, and again, sine has this, the sine function has oscillating signs, S-I-G-N-S. So the minus, plus, minus, plus, minus, plus. And here's the expansion for the exponential function. It's very similar to cosine and sine, except we only ever are adding these terms. We get all the powers, these powers of x starting from x to the 0, x to the 1, x to the 2, 3, 4, etc., with denominators of these factorials. Okay, so I think those are beautiful identities right there. But even more so, so it almost looked like sine, or cosine x plus sine x gave us the exponential function, but not quite. But what we do is we can set I to be equal to the square root of -1. So what does that mean? Well, it means I is just this symbol, so that I squared is -1, so then I cubed is minus I to the 4th, well that's I squared, so that's 1. And then the values just start repeating again. I to the 5th, well that's I to the 4th times I, so that's just I, and so on. And so if we take our expression for the exponential of x and we substitute for x, ix, well what do I get? The 1 stays the same, and then x is replaced by ix. X squared is replaced by ix squared. I squared is -1, so oops, there it is. I get the minus x squared over 2 factorial. X to the cubed over 3 factorial. I replace x with ix, and so I get minus I times x cubed over 3 factorial, and so on. And so what we see are the terms that I have in green, which I hope looks like green to you. That was our expansion for cosine of x. And the terms that I have in blue is almost our expansion for sine of x, but all those terms are multiplied by an I. And you notice that the signs, the pluses and the minuses, oscillate the way they should for cosine and sine, and so we get the identity that the exponential of ix is equal to cosine x plus I sine x. And that's my QED box. It's a fish. Okay. Another theorem that a lot of people, certainly according to the internet, have cited as a very beautiful theorem is the Pythagorean theorem. And so it says that if we take a right triangle, so that means this is a right angle, it's a 90-degree angle, and we say that one leg has length A, the other leg is length B, and this hypotenuse, well, let's call that length C, then we've got the relation that A squared plus B squared equals C squared. Okay. Now I'm going to show you a proof. There are lots of different proofs for this, but I'm going to show you one that's particularly elegant, according to a lot of us. So what I'm going to do is I'm going to begin with this square whose sides have length C. And then into that, I'm going to inscribe 4 copies of that right triangle I had before. So here's one of them. So that's length A, that's a right angle there. That's length B, and then its hypotenuse is length C. Here's another one of the right triangles, length A, length B, length C, and so on. And then we're left with this square in the middle. We can tell that that's a right angle because that's a straight line, and that's a right angle right there. Okay, so it's a square, and what are the lengths of its sides? Well, this is length B from our right triangle with one longer leg of length B, and this piece here is the leg of this triangle that has length A, so what's left for this length is B minus A. Okay, but overall we can see that this square has area C squared. Okay, but now I'm going to rearrange it. So this triangle used to be up here in our previous picture. I've also rotated it so it would fit on my slide. So what did I do? I pivoted this triangle from where it used to be at this corner. So if I pivot again, I could move it back up like that. And this triangle used to be up here. And I pivoted it on that corner to move it down here. But now what do I have? Well, this side is length B. This side is length B minus A, we determined. This side is length A because it's a leg of this right triangle. It's the shorter leg. So the total length there is B. So here I have a square. That's B by B. And over here, I have this length is A. It's the shorter leg of that triangle. This total length is B plus A, because that's length B, that's length A from this triangle. And so here is length B, this total length across that whole thing, what happened to my guy, is A plus B, but here's B, so what's left over is A. So this is a square with side length A. And so the total area of this object is a squared plus b squared. Okay, but it's made from the same pieces that made up this square of side length c. So we have exactly the same pieces, just arranged to give us a square, and here arranged to give us two squares, and that gives us the identity that a squared plus b squared is c squared. And those are my own watercolors. Okay, so now let's ask a more general question. This is what pure mathematicians like to do. We solve one problem and then we say, ooh, can I do that more generally? So we call a triple of integers, positive integers, a Pythagorean triple when the triple ABC satisfies the identity a squared plus b squared equals c squared. So here are the positive integers. Just 1, 2, 3, 4, 5, so the counting numbers. And here's an example of a Pythagorean theorem, a Pythagorean triple. So we take a to be 3, b to be 4, and c to be 5. And then a squared plus b squared, well, that's 9 plus 16, which is 25. And that's 5 squared, which is c squared. And you can mess around and find more such triples. But then we can ask the question, are there infinitely many Pythagorean triples? Okay, pure mathematicians like to count. Now, the most important ways of counting, or counts that we have, are 0, something doesn't exist; 1, it exists and is unique; infinitely many; or, something finite but not 1. Who cares what it is, you know? It's in between. Okay, well, first of all, what we can notice is that Pythagorean triples stratify into families. And each family is generated by a particular Pythagorean triple called primitive. Oops, that's getting ahead, using the wrong thing. Okay, and so this Pythagorean triple will be called primitive if the highest common factor of a and b is 1. Okay, so then if I multiply every one of those elements, the a, b, and c in my triple, if I multiply each of them by some number k, let's take k to be a positive integer, that gives me another Pythagorean triple. Easy identity to check. And so already, just from this one primitive Pythagorean triple, and I showed you that at least one exists, we get infinitely many Pythagorean triples. But even more, Euclid developed an algorithm to show that there are infinitely many primitive Pythagorean triples. So there are infinitely many families of these Pythagorean triples. And here is a picture of them plotted. Look it up on Wikipedia to understand how these are arranged. It's little, I couldn't fit on the slide describing what arcs these are arranged on, but looks pretty cool. So this is just a close-up of a piece of this, which looks almost symmetric, but you've got these holes in places. Some dissonance makes it more interesting. Okay, so now I'm going to modify this question some more. So we're looking at Pythagorean triples. How many ways can you find positive integers a, b, and c so that a squared plus b squared is c squared? Well, I'm going to ask the question, if I just take a positive integer n, how many ways can I realize n as a sum of two squares of integers? Okay, and now I'm going to allow negative integers as well, and 0. So the integers in blue here are the positive integers, which we looked at before, but now I'm going to look at all the integers, basically because the set of integers has some nice mathematical properties. It's a ring, as we know from Algebra 2. And we got 0, -1, -2, -3, -4 in there. Okay, and generalizing even further, how many ways can I write n as the sum of k squares of integers? Okay, so here's an example of doing this. If I take n to be 12 and k to be 8, so I want to write 12 as a sum of 8 squares of integers. So one way I can do it is 3 squared plus 1 squared plus 1 squared plus 1 squared, and then I add zeros to have 8 terms. I can use 3 squares of 2, and then I use zeros for the other terms. 2 squares of 2, 2, 3, 4 squares of 1, then add zeros. Okay, so those are 3 ways of writing 12 as a sum of 8 squares of integers. But I can take one of those ways, that was the first way I did it, and I can use that to make other solutions. For instance, I could replace this 3 by a -3 because when I square that, I get the same thing. Or I could rearrange. I could swap the order of 3 squared and 1 squared, like I do here. And I can take all sorts of combinations of that, changing the sign, swapping the order. So really what I'm counting are the number of ways to write 12 as an ordered sum of 8 squares. Okay, and just from those initial 3 solutions that I showed you, you start changing the signs and rearranging the order, and you find that there are 31,808 ordered ways, or ways to write 12 as an ordered sum of 8 squares of integers. Okay, that's a lot to count. And I want to introduce some notation to make it a little easier to talk about this problem. So I'm going to use this notation r sub 8 of n to denote the number of ways we can realize n as the ordered sum of 8 squares of integers. And then I have a formula for this. So this formula in the box says that the number of ways to write n as an ordered sum of 8 squares is 16 times this sum, where I'm going to vary this guy d over all the positive integers that divide n, and corresponding to each one of these positive divisors of n, I have in this sum the term -1 to the n minus d times d cubed. And this formula works for any positive integer n. Okay, so there's my formula again in the box. So let me look at an example of using this formula. So I take n to be 12. We already saw a different way of arguing what r sub 8 of 12 is. So the positive divisors of 12 are 1, 2, 3, 4, 5, 6, 12. And so now I look at my formula, well, the sum from my formula. So I take my first divisor, take d to be 1. So I have -1 to the 12 minus 1. So I have -1 to the 11. So that gives me a negative, times 1 cubed, so I just get -1. Now I take the divisor 2. So I have -1 to the 12 minus 2. So I have -1 to the 10, that's just 1, times 2 cubed, so that gives me the 8. Then I go to the next divisor, 3, and I put 3 in for d. This gives me a -1, this gives me a 27, that gives me the -27, and so on. And so this sum right here gives me 1,988. Now my formula says multiply that by 16, and I get the number of ways I can write 12 in this case as an ordered sum of 8 squares, and I get the same answer, yay, 31,808. Okay. So there's a similar but more complicated such formula for realizing how many ways we can realize a positive integer n as an ordered sum of 6 squares. Ooh, some more dissonance, maybe more interesting. So this is our formula, and this works again for any positive integer n, just this rather simple formula. It's complicated by this chi of d in here and chi of n over d. This is something we call a character. And here's how chi of d is defined. It's 1 if 4 divides d minus 1. It's -1 if 4 divides d minus 3, and it's 0 otherwise. Okay, so let's look at an example of this. Let's look at the number of ways we can write 12 as an ordered sum of 6 squares. Okay, so first let's figure out what chi is on the positive divisors of 12. Chi of 1 is 1 because 4 divides 1 minus 1. Chi of 2, that comes out okay up there, good. Chi of 2 is 0 because 2 is even. Chi of 3 is -1 because 4 divides 3 minus 3. Chi of 4 is 0, chi of 6 is 0, chi of 12 is 0. So there aren't going to be many terms, and many non-zero terms in my formula for R6 of 12. And what do we get? Okay, so here, the 16, and now I'm going to add the squares modified by this chi of 12 divided by d. So D has to be one of these divisors so that 12 divided by D is odd so that we get a contribution. Okay, so what does that mean I can do? I can take D to be 4, and then 12 divided by 4 is 3. That gives me a minus from the chi of 12 over 4. And then I get D squared here in my formula, so that's 4 squared. I could also take D to be 12, and then I have chi of 1 times 1 squared, times 12 squared. That gives me plus 12 squared there. And the other term, I have a minus 4. And now, again, I have to take D to be the odd positive divisors of 12. And so I get the 1 cubed minus 3 squared. And there I have a nice formula. Okay, so more formulas. There's one for, go back. The number of ways to write n as an ordered sum of 2 squares. That's the same chi as I showed you before. N as the sum of 4 squares, 6 squares, sorry, we did 6, we did 8, so now I'm on to 10. And here I've got the first 2 terms in my formula are nice and neat, and then I have what I've written as noise, and I have something similar for writing n as an ordered sum of 12 squares. What do I mean by noise? Well, as n gets really big, by comparison to the first 2 terms, that noise gets really small. Okay. Now, before I talk about how we get to such formulas, let me ask, why is it natural to even consider this question in the first place? Okay. Well, that doesn't show up so well on there. It did when I tested in another room. Here I've got a right triangle. So this point I'm labeling as x comma y. So this length is x, this length is y. And now x squared plus y squared is the square of the length of this side of this triangle. And so using these sums of squares, we can capture some notions from geometry. So I take a point xy, and I think of this vector, so this side here as being a vector joining the origin to the point xy. And again, the length of this vector, or the square of the length of the vector, is x squared plus y squared, a sum of 2 squares. And we can generalize this to m dimensions. We identify any point with coordinates x1, x2, up to xm. We give it coordinates relative to perpendicular axes. And then I put a little arrow over v, my point, to denote the vector that joins the origin to that point. And then I'm going to introduce a dot product because I want to talk about another aspect of capturing geometry. So the dot product of v with the vector v with itself is the sum of the squares of the coordinates. Okay, and by the generalized Pythagorean theorem, this is the square of the length of that vector. Okay, we generalize the dot product, so a lot of you will have seen this in a physics course. So if I take another point w with coordinates given by y's, and I look at vector v dot product vector w, x1, y1 plus x2, y2, etc., and what we find is that these 2 vectors are perpendicular exactly when this dot product is 0. Okay, so this dot product is capturing geometry for me. I'm going to come back to that at the very end. So, why is it natural to only consider the sums of squares of integers? Well, a lot of the systems that we really care about are discrete. So, like in the digital economy being one of the most popular examples these days, we think of representing things using pairs, this in 2 dimensions, pairs of integers. So here I've drawn a grid. So this is supposed to be length 1, length 2, length 3. And everywhere the grid crosses has an intersection, I put a vector there. So there's a point where it crosses. Think of those as my vectors. And so to represent a lot of these discrete problems, we use a system that I can draw in this way. Okay, now let me go back to where these formulas come from. So when we look at sums of 6, 8, 10, or 12, or higher even powers, higher even positive integers. These formulas come from the theory of modular forms in Theta Series, which is where my research lies. And so what's a Theta Series? Well, what I do to build my Theta Series is I'm just going to build like an infinite degree polynomial. So z here is my variable for my polynomial or my series. And the coefficient on z to the n is r sub k of n, the number of ways to write n as an ordered sum of k squares of integers. Okay, so all I've done is write down a sum that has as coefficients these numbers I want to understand. But using the geometry that's captured by the dot product, I can show that this function that I've called the Theta series is a particular sort of function. It's a nice kind of function. It's called a modular form, and the weight that it has, this is an invariant attached to it, is half k, where k is the number of squares we're interested in. Okay, how does this help? Well, when k is 8, we're looking at a modular form of weight 4, and I know I know a basis for the modular forms of weight 4. I know I can write any such thing, like in particular this theta, as a sum of these, a weighted sum of these three functions that I'm calling E1, E2, E3. And what do those guys look like? Well, E1, again, it's like an infinite degree polynomial, has some constant, I don't care. But then the coefficient on z to the n is given by this sum. It's just positive divisors of n that are odd, and the sum of those guys cubed. Okay, E2, similar shape, except now I'm only going to sum over those positive divisors of n, where n over d is odd. And E3, similar kind of sum, except I'm only going to sum over those positive divisors d of n, where d is odd and n over d is odd. Okay. Then by brute force, like we did when we were looking at how many ways can we write 12 as an ordered sum of 8 squares. So by brute force, we can compute that the number of ways to write 1 as an ordered sum of 8 squares is 16. For R8 of 2, it's 16 times 7. R8 of 4 is 16 times 71. And that's enough information to figure out what the coefficients in this relation have to be. So this function here has to be some weighted sum of these guys. But I can figure out from these equalities what A, B, and C have to be. So A has to be minus 240 over 7, B has to be 128 over 7, and C has to be 32. Okay, and then it's kind of a fun exercise for those of you who are math students to go from the formulas for E1, E2, and E3, and those coefficients A, B, and C, to rearrange and find that we get the formula I claimed in the first place. Okay, and the process for finding the formula for R6 of n is similar, but for R10 of n and R12 of n, we have to be a bit more sneaky. Okay, so what we do is we build from the guy we really want to understand, we add some noise so that we get sort of a smoothed version of this. And now this smoothed version, I can argue using the theory of modular forms, has to be a linear combination, a weighted sum of these two functions, E1 and E2, where now E1 and E2 have coefficients like this, still pretty nice and neat. That's that same chi that we saw before. And then we use information about the behavior of these three functions, my smoothed theta series, E1 and E2. We use information about those guys at infinity, which I'm not going to explain, gets a little complicated, to find these values of A and B, and we get this formula, that my smoothed theta function is this combination of E1 and E2. Now that smoothed guy is almost the guy we wanted. It's off by noise, so that tells us that the guy I really wanted is this combination plus some noise. So that's where that formula came from for the number of ways to write a positive integer n as an ordered sum of 10 squares. So my research, just very quickly here, I am going to change the geometry in my setting by changing how I define the dot product. So I can replace it, for those of you who know some of this math, I replace it by any quadratic form, presuming that it's positive definite, meaning I want my non-zero vectors to all have positive length in that geometry. And so then I ask, in my mother lattice, so my big grid that I drew before, how many vectors in there have a given length? Okay, and then more generally I can ask, well, what if I take a sublattice? How many sublattices of my big lattice have that same geometry? Okay, so sometimes I can't get precise formulas, but I can get relations among these things, like this, which is supposed to look sort of pretty. You know, maybe some dissonance, but that's more interesting. So it's nice and neat. So P here is a prime. 2K is the dimension of my lattice, my big lattice. T here is the dimension of the sublattice that, oh, I'm trying to count how many sublattices have the same geometry as some given lattice of dimension T. Now, R of lambda is going to be the number of sublattices contained in my big lattice with the same geometry as lambda. But I'm not going to get such a nice formula if I just work with that. So I use a smoothed version. So this is an averaging. So I smooth out the count that I really want. And so it's off by noise. But then I get this nice pretty formula. Oh, that's an exponent that I can describe precisely, but who cares? It's explicit. Okay. And so what I hope I might have convinced you of is that, certainly for me, being a mathematician feels like kind of being an archaeologist, where I'm just trying to sift through what's there and find the underlying structure. And it's really exciting when you find that. You look at something like, bleh, how could there possibly be some nice formula that I can describe whatever I'm looking at? And so when you find that, it's wonderful. Thank you.